Now we're going to move on to stoichiometry, limiting reactants, and percent yield. Now, stoichiometry, if you remember, is the study of quantities of materials that are consumed and produced in chemical reactions. So we look at how much reactant are we using, how much product are we forming. It's the whole basis of stoichiometry. Stoic is the most important thing you can learn in AP. So starting off AP, start strong with stoichiometry. If you need extra practice, do extra practice in the book. Go through the sample problems, do the odd problems, look at the answers in the back, but get good at this and you will be pretty much good all year. Stoichiometry never goes away, ever. When we're talking about gases, you're going to have to do stoic. When we're talking about intermolecular forces, you're probably going to have to do stoic. So just make sure that you get really good at stoichiometry. So going along with these stoichiometric calculations, we talked about coefficients in lecture 1, but the coefficients of a balanced equation give you your mole ratio. So they give you your ratio of one reactant to the other reactant or one reactant to product. So it's very, very important that you balance your equation because your coefficients give you your number of moles. So we've already seen how to convert from grams to moles or moles to grams. What's new here in stoichiometry is comparing two different things, right? So comparing substance A to substance B, and that's using the mole ratio from the balanced equation. Starting with the mass of substance A, we can use the molar mass to get to moles, then we use the mole ratio to get to moles of B, right? So that's why converting everything to moles is so important, because your coefficients tell you moles. Your coefficients do not tell you grams. Now your coefficients tell you moles. So that allows you to go from A to B, and then we can use molar mass or Avogadro's number to get to whatever other unit we need. So what we're actually going to do is we're going to go through an example of one of these calculations, but I'm going to show you two different methods that you can use to go about solving stoichiometry problems. Now, the preference is up to you. I don't care which one you use. Your book kind of goes back and forth, but it's up to you with whichever you use. So the example that we're going to go through says how many grams of water can be produced from 1 gram of glucose. So before I even worry about solving anything, I'm going to circle what I'm trying to find and underline my given. Now you notice I circled grams of water, not just grams. So I know that I need to get to grams of water, and I'm starting with grams of glucose. No matter which method you use, you always have to convert to moles. So no matter what, convert to moles. Now if you notice that you have water here and glucose here, it's probably going to be helpful to find the molar masses of both. So if you want to find the molar masses of both before you even start, that might be helpful, and then you can put them in parentheses just to kind of help you as you work through. So what we're going to do is we're going to start with method 1, we'll work through the problem, then we'll go through method 2. Method 1 is going to be solving this problem using dimensional analysis. Now this is probably what a lot of you have done with solving stoichiometry, is you just go through using this dimensional analysis, and that's fine, but I still want to go through it. The first thing you want to do, before you even worry about math, make sure you have an equation, make sure it's balanced. That's always going to be the best thing to do. We already have the equation, it's already balanced for us. The next thing we need to do is we need to take our given, which if you remember was 1.00 grams of glucose, and we need to convert it to moles. Remember, with any dimensional analysis, the unit you're trying to cancel goes on the bottom. I'm sure I'm going to run out of space because my writing's too big. Then I'm going to go from grams to moles. Alright, so 1 mole, and this is why I wrote the molar masses up here. For every 1 mole, it's 180.18 grams. That never changes. Molar mass is always for 1 mole. So what I'm going to do is, let's take my calculator, 1 divided by 180.18, and we get, remember, leave a little bit of extra significant figures. I'm just going to solve this now. 0.00555 moles of glucose. Now, again, the reason I solved it here instead of just working through it all the way is just because I didn't have the space. So 0.00555 moles. I'm at moles of glucose now. Is that what the problem asked me for? No, it asked me for water. So somehow I need to get from glucose to water. Well, I'm at moles of glucose. These coefficients compare moles. For every 1 mole of glucose, I actually make 6 moles of water. My moles cancel, I'm at moles of water. Does the problem ask me for moles of water? No. I have to get somehow from moles to grams. Well, again, for every 1 mole, 18.02 grams. Sorry, this stylus does not work very well with my writing. So we're going to take our answer, this 0.0555, multiply it by 6, multiply it by 18.02, and we get, let's write it in blue so you can see, 0.600. Initial are given, had 3 sig figs. My answer needs to have 3 sig figs, grams of H2O. So if I start with 1 gram of glucose, if I burn 1 gram of sugar, I make 0.6 grams of water. Okay, so that's how we work through with dimensional analysis. Now, you may have started here and just worked through all the way. You know, you didn't solve right here, you just kept going. That's fine. You just make sure all of these units cancel, you get what you need, include units and a substance on your answer, and you're good to go. So this is the first method of using dimensional analysis. Okay, so we looked at solving this problem using just dimensional analysis, and now we're going to look at solving this using what's called a BCA table. BCA stands for before, change, and after. Now your book kind of mixes these two methods. Sometimes you use the BCA table, sometimes they use just dimensional analysis. So I want to show you both methods. Again, the method that you prefer and that you choose to use is solely up to you. I don't care which one you use, but you want to make sure whichever you use, you're very consistent. Now, with this BCA table, again, I said it's before, change, and after. When you put anything into this BCA table, the only thing you can put in is moles. Okay, so if you're given grams, you have to convert to moles before you can put it in the table. This table is just a way for us to visually organize all of our information. From the last problem, we said that our given, which is 1 gram of glucose, we solved it for moles. You do it the same way, right? 1 gram, 180.18 grams is 1 mole. Okay, and remember that was 0.00555 moles of glucose. The problem says nothing about oxygen and nothing about carbon dioxide. So we're just going to cross those out just to remember that we're not working with that at all. This is before the reaction even takes place. So we have our given, but we also need to look at our before for water. So before the reaction even takes place, do we have any water? No. We have 0 moles of water. This change is probably the most important row in this table. This change takes into account these mole ratios. Our glucose is 1. That means that for every 1 mole of glucose, we make 6 moles of water. However, do we have 1 mole to start? No, we have 0.00555. Now, this is where these ratios come into play. Glucose is our only reactant. We're going to assume the reaction goes to completion. So we use up 0.00555 moles of glucose. Notice this negative sign. Your reactants get used up, your products get formed. So after the reaction, we have no glucose, but we have to figure out how much water we have. Is the glucose to water a 1-to-1 ratio? No. For every 1 mole of glucose, we have 6 moles of water. So what we can do is down here, set up a problem for every 0.00555 moles of glucose, how many moles of water do we have? If for every 1 mole of glucose we have 6 moles of water, this is where these mole ratios come into play, we simply multiply our number by 6. Okay, when you multiply that number by 6, you get 0.0333 moles of H2O. Does the problem ask you for moles? No, it asks us for grams. So now what we have to do is just convert this to grams, multiply by the molar mass, and just like in method 1, we're going to get the same answer, 0.600 grams of water. Okay, so notice this is just another method to use. Typically, when I go through examples, I'll probably just do it using dimensional analysis. When these BCA tables really come into play is when we look at limiting reactants. This allows us to visually organize everything to see which reactant is limiting and why. So I just mentioned limiting reactant as we were working through a stoichiometry problem. Limiting reactant is just your reactant that's present in the smallest amount, right? It's the one that limits the reaction. So in other words, it's the reactant you're going to run out of first. In this example down at the bottom, okay, we have hydrogen and we have oxygen. This particle diagram, again, I've been mentioning it throughout this entire chapter. You have to know how to use these particle diagrams. We have hydrogen and oxygen. So the red is oxygen, the white is hydrogen. In this case, hydrogen is what is limiting, right? It's what you run out of first. That means oxygen is your excess reactant. Now, when you're looking at limiting reactants, a way to tell if you have to determine the limiting is if you're given 2 amounts and 2 reactants. If you're given an initial amount for every single reactant in the reaction, you're going to have to first determine the limiting reactant. The problem might not always specify to determine the limiting, but that's one thing that you want to make note of. The limiting reactant is what is used in all of your stoichiometry calculations to determine the amount of product, because it's the one that limits the reaction. The theoretical yield is something that's very, very important as we look at laboratory calculations, because there is a difference between theoretical and actual. The theoretical yield is the maximum amount of product that you can make. Typically, this is what you calculate. Theoretical yield is all done through calculations. And then you have the actual yield. This is what you get in the lab. This is what you actually get in the lab. Either it's measured in the lab, or sometimes the problem might just give it to you. It might say, you know, this is what you measured in the lab. So theoretical, based on calculations, actual yield, what you get in the lab. So going along with this theoretical and the actual yield is calculating percent yield. This is really important when you're doing any gravimetric analysis or when you're doing any stoichiometry based lab. Your percent yield is just comparing what you got in the lab to what you were supposed to get. So when you're finding percent yield, percent yield equals actual, which is what you get, over theoretical, which is what you calculate. So again, actual lab-based, theoretical based on calculations. And don't ever forget that if it is a percent, multiply it by 100. Okay, so that's it for chapter 3. Remember, a lot of the examples are scanned through that QR code. So please work through every example. If you need help with it, scan the QR code, watch the video. You know, if you need to work through every calculation, just take the time, watch every video. If you're good with everything but maybe limiting reactants, I do go through a limiting reactant in 3 different methods, one of which is typically used more than the other, but it's very, very important that you see all of the methods. So I would definitely recommend watching the limiting reactant as well as the combustion analysis, just because the combustion analysis is new. If you find that you have any questions, please email me, let me know, and I can answer your questions as you're working through the notes or the homework.